So today we're going to do the divergence theorem, and it's asking evaluate both integrals of the divergence theorem for the following vector field and region. So you have integral A, the first one, and D, the second one. So practically the first integral of the divergence theorem comes in this format. D, then you got lambda, not lambda, but inverted triangle, the dot product of f dv, whereby this is the volume. And we know that this is pretty much the divergence of the integrals. So basically, we're going to have to find the divergence of f in this case. So the divergence of f is, we know it's going to be del x, no, del f, del x plus del g, del y plus del h, del z, which in other words is going to be del f del x, that's going to be 3 plus 2 plus 2, which gives you the gradient field as 7. So far so good. So this is going to be our first integral, whereby we're going to have to find all that brought to the 7dv. Okay, so since this integrand is a constant itself, so it's independent of the coordinate system, so meaning that we can take this outside such that we're gonna get, say, 7 d dv. Okay, so we know that since, like I said, this is dv, so this stands for the volume. Because then again, we have 3 dimensions. We got x, y, z, and this pretty much, like a sphere. So it's all 3D in this case. So therefore, we're going to find the volume of D. And given that we have this equation over here, x squared plus y squared plus z squared, all this is equal to z, no, not z squared, but r squared. And you got r squared is equal to 4. So implying that r is equal to 2, because basically r squared square root. Okay, so far so good. So practically we're gonna multiply the volume of the sphere with this radius as 2 and by the constant integrand of 7. And basically we know that the volume of a sphere is equal to 4 pi r cubed, right, over 3. So in this case, we're just gonna do 4 pi r cubed, which in this case is 2 cubed, that's gonna be 8 over 3 times 7. And the answer you're gonna get in this is gonna be equal to 224 pi over 3. Okay, so that's not it yet. The second integral of the divergence theorem is given by, let me get my pen. So this is integral 1, So 2, the second integral is going to be given by s f dot n ds. And f and n, so these two guys must be expressed in the same coordinate system. In this case, we're talking about a sphere, and we're going to have to parameterize it in the form of, say, so I'm going to add parameterizing the sphere into the form, let's see, that's going to be a sine u cosine v, a sine u sine v, and a cosine u. So that's 1 dimension, 2 dimension, 3 dimensions. Okay. So in this case, our A is gonna be our R. So let me get my green pen. And for this question, R is gonna be, so plug in 2 for every value of A. 2 sine u cosine v, 2 sine u sine v, and sorry, that's 2 cosine u and 2 cosine u. Okay, so for the surface that is determined parametrically in the region R, this function over here, or this integral, can be evaluated using, let me get my pink pen. So this s f dot n ds is the same as, taking r f dot tu times tv, whereby tu is gonna be dr du, and tv gonna be dr dv, right? Drink some milk.